In this A-level chemistry video, we're going to look at the Henderson-Hasselbalch equation. What it is, where does it come from, and how can you use it to make buffer calculations a little bit easier. We should probably start with a bit of a public health warning. So for AQA A-level Chemistry, the Henderson-Hasselbalch equation isn't actually in the specification. And part of the reason for that, I guess, is that really there are 4 different versions of the equation. And it can be really easy to get your working completely wrong if you've been looking at lots of different resources and seeing this written in lots of different ways. So if you are going to learn to use this equation, you need to settle on one particular version of it and make sure that you are always using that particular version and not veering off. So the version that I like best, because it fits with how I derive it, is pH is pKa take away the log base 10 of the concentration of acid divided by the concentration of salt. Now, you might be looking at that equation and thinking, well, this is another equation to learn. It's not listed in my specification, and is this really going to make my life any easier? Not necessarily, but I think it's really useful to have a trick up your sleeve to check your working. So I would always suggest that you work out the pH of a buffer longhand. However, if you know your Henderson-Hasselbalch equation, then you can use this at the end to check your answer, and if you get the same answer from both methods, you know there's a pretty good chance you've done it right. There's also a couple of other reasons you might want to use this equation. One is that quite often in a question, or just, when you're doing chemistry in the real world, you're going to be given pKa rather than Ka because it's just a nicer number. And the other thing is that occasionally you won't know the volumes that you're working with, and if that happens, then this is really your only option. So although the equation is expressed in terms of the ratio of the concentration of acid and the concentration of salt, those two things are dissolved in the same volume of liquid. And that means that that same ratio of concentrations will match up with the ratio of the moles. And so actually, if you know the moles of them, even if you don't know the volume that they're in, you can still use this equation. But for now, let's just concentrate on where on earth this equation has come from. You're already really familiar with Ka, and you know that it can be expressed in terms of the concentrations of hydrogen ions, anions, and the undissociated weak acid. In other words, hydrogen ions multiplied by salt over acid. And of course we can rearrange that expression to make hydrogen ions the subject. Now you know that for any equation with an equal sign in the middle, I can do whatever I like to the left-hand side, as well as I also do the same thing to the right-hand side. So if I want an expression in terms of pH, and I'm going to sort of take the P of the hydrogen ion concentration, then I need to take the P of the right-hand side as well. And right now you might be thinking, well, what on earth does it mean to take the P? That's not a mathematical term. Well, how would you work out pH from hydrogen ion concentration? You would take the negative log base 10. So that's exactly what we're going to do. We're going to do the same thing to both sides of the equation. So now I have a new expression where pH, which we know is negative log base 10, is the negative log base 10 of Ka multiplied by acid concentration over salt concentration. Now, Ka is often expressed in terms of pKa because it's just going to be a nicer number, just like how we have pH rather than using teeny tiny numbers and actually giving hydrogen ion concentration. So I want to get that Ka term out as a pKa term. Now, if you're taking A-level maths, then you should know that the sum of 2 logs is the same thing as the log of the original 2 numbers multiplied together. In other words, if we want to pull out that Ka term, then we can say that pKa plus the log of our acid divided by our salt is the same thing as the original log of the original equation. So we can have something that looks a little bit like this. And now we've got our original Henderson-Hasselbalch equation. One thing that's really important to note is that we're taking the negative log base 10 of the ratio of the acid and salt concentrations. We're not taking a negative log base 10 of acid and taking a negative log base 10 of salt and then dividing those. We're doing the ratio first and finding the log of the ratio. And it's really important you get that right, otherwise you will end up with completely the wrong answer. So here we are back at our Henderson-Hasselbalch equation, and the only thing that's slightly different is that rather than bothering to write plus negative log, I've just written take away log, but otherwise it's exactly the same equation. So now let's look at a couple of examples of how we can use this. We're going to look at 2 quick questions, and as I said before, I would make sure that in the exam you are solving these using the full method, because that will get you working out marks if you don't get the right answer, but this is how we're going to check our answer at the end. So in this question, we have a pH buffer made from ethanoic acid and sodium ethanoate, and we've been given a value for Ka. So when I do my checking, I'm going to write out my equation for Henderson-Hasselbalch, and then I'm going to calculate a value for pKa. Sometimes I would be given that in the question, but in this instance, I haven't been. So I know that to work out the P of anything, I do the negative log base 10. So the negative log base 10 of the Ka for ethanoic acid is 4.77. So I can immediately substitute that into my equation. And then I'm going to need to work out my concentrations of acid and salt. Now in this question, I haven't been given the volumes, so I can't sort of work out the moles and then add the volumes together and go the long way round, but I've been told that we're adding equal quantities of ethanoic acid and sodium ethanoate. So because for each one of those two chemicals the volume has doubled, the concentration is going to have halved, so I get 0.2 and 0.05. Now remember, it's really important that I work out 0.2 divided by 0.05 and then do the negative log base 10 of the whole lot. I'm not going to do a log for each one of those individually. So this ends up with 4.77, take away 0.60, which gives me a final answer of 4.17. And if you do this calculation longhand, you will get exactly the same answer. Here's one more for you to have a go at, so pause the video, work your way through, and then we can check your answer at the end. My first step was to write out the Henderson-Hasselbalch equation, and then to work out a value for pKa by taking the negative log base 10. So that gives me an answer of 3.74, which I can substitute into my equation. Again, here we've got equal volumes of the two chemicals, so for my concentrations, I'm just going to half them. And then once I've worked out that 0.2 divided by 0.3 is 0.66666, I can work out that I'm going to have 3.74 take away negative 0.18. So of course those two minus signs cancel out and I'm basically just adding 0.18 and I get a final pH of 3.92. Thank you very much for watching, and I hope you found that a useful introduction to the Henderson-Hasselbalch equation. As I said, I would definitely recommend learning the long form method of answering these questions, but this is a really useful way of checking your answers in the end. If you did find the video useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.